Okay, so we are going to start with the chapter on oscillations in your book, and this is chapter 14. And let's start by looking at oscillatory motion. And basically, it's any motion that looks like this. If you plot the position versus time, it basically is a cycle, a motion made of cycles. It always comes back. So here it starts over here, comes up here, then back down, and comes back to the same point. This is a type of oscillatory motion. You can have something like this, or you can have an oscillatory motion that look like this. So there are two quantities here that we need to be aware of. One is the period, and the period is the time that it takes to go from the initial point right here until it gets back to the same point. All this time that it takes to go, that is the period. And then here, there's a new period. In this case, would be starting here and comes back to the same point. That's a period. In this case, the period could be starts here and then comes back to the same point. The time that it takes for the object to come back to the same point, that is the period. The period. The frequency is the number of cycles per second. The frequency is measured in hertz. The period is measured in seconds or any unit of time. 1 hertz is 1 cycle per second. For instance, your heart beats about 60 times per second. So the frequency of your heart is 1 hertz, and the period is just 1 second. So let's see. Let's calculate the frequency of a loudspeaker. The speaker vibrates back and forth 5,000 times per second. The oscillation of the frequency then is 5,000 cycles per second, or 5,000 hertz, or 5 kilohertz. The period is the inverse of that frequency. And remember, it's the time that it takes to go back and forth to the same point, right? So it's 1 over the frequency, and it's 1 over 5,000 hertz, which gives you 200 microseconds. So one type of oscillatory motion that is important and that we are going to study is the simple harmonic motion. A simple harmonic motion, and let's just look at a simulation. A simple harmonic motion look like this. So here we have a mass that is going to oscillate, and here we have a simple harmonic motion. It goes back and forth, so it starts here, then goes all the way here and back. That's the period, and the frequency would be given by the number of these cycles per second. If we were to plot this motion, if we were to plot it, this is how it would look like. So this is the position versus time. This is the position versus time. Here we have velocity versus time. And here we have acceleration versus time. Notice that at the time the velocity is maximum, at the time the position is maximum, the velocity is minimum, is 0. All right, so that is a, a simple harmonic motion. The definition, this is, for instance, this is a picture of a mass in an air track, and this would be the plot of the position versus time of the mass. It goes from a maximum amplitude to the negative of that amplitude. This distance from here to here, from here to here is called the amplitude of your motion. So which one of these oscillations is harmonic? Take a minute. And the answer is known. Remember, a harmonic oscillation looks like this one here. So here we have again a plot of position versus time, and down here we have velocity versus time for a harmonic motion. Things to notice: this distance from here to here, that is the amplitude. The period is the time that it takes to go from here to here. The frequency is the number of cycles per second. And notice that here I have a maximum position, and at the same time the velocity is zero right here. At this point I have maximum velocity, and at that point the position is zero. So the velocity is zero at the times when the position is maximum, and the speed is maximum at the times when the position is zero. So if we have an object and we release it from rest, right? And then this is the position versus time, and we plot that. So the graph that we are going to obtain is the graph of a cosine or a sine, where A is the amplitude, is the distance from this point to this point, and omega is called the angular frequency. The cosine and also the sine are sinusoidal functions. This omega here, we call that the angular frequency, and is related to the period by 2 pi over t over the period, and related to the frequency by 2 pi f. So the simple harmonic motion, the equations, if we use the cosine, for instance, this is the position, is a cosine omega t. The velocity is the derivative of the position with respect to time, which is a times d dt of cosine omega t. That gives me a minus sign with an omega that comes out of the function. So you get that the velocity is minus a omega sine omega t. This is the maximum position a, and the maximum speed is a omega. So here we have the plot of position versus time. So remember, this is the period, and you can see right here, this is when the position is maximum, or here when it reaches the negative maximum here. And at those points, the velocity is zero. Every time you see the velocity here being zero, the oscillator is reaching a maximum. Let's look at this in the simulation again. In the simulation we had, let's reset this. So we're going to start from here, and then we go play, and you can see now that, let's just reset this and then pause, and then let's step slowly right there. We have a maximum, right? That is the maximum. The velocity right there is zero or almost zero. We continue, we continue. That's the maximum velocity right here, and the position is zero right at this point. And let's see what happens when we change the frequency. We have now a frequency of, and now you can see that it's less cycles per second. The period is longer. So the if you decrease the frequency, then you have less cycles per second, the angular frequency. Okay. So these are the important plots of the simple harmonic motion. And this is what we need to remember, and we're going to study how to use these equations in this week and next week.